In this last set of lectures, we're going to be looking mostly at how we name compounds or how we can go from name to structure or structure to name. But to do that, I want to just lay a little bit of a foundation. Some of this I've talked about sporadically um, through various lectures, but I'm going to kind of organize it all. And so I want to look at how we categorize pure substances. So we break pure substances up into one of two groups. Elements, which these are things that consist of one type of atom, and compounds. And compounds contain more than one type of atom. And with elements, we either have atomic elements, which are just one atom, like the noble gases, for example. Or there's molecular elements, which have more than one of the same atom. And I've highlighted this before. Some of the most common ones are the diatomic elements, like hydrogen, nitrogen, oxygen, and the halogens. And within compounds, we've talked about two different types of compounds: ionic compounds, which again consists of a metal with a nonmetal, like sodium chloride, combining a sodium cation with a chloride anion. And then we've looked at covalent compounds. These involve uh, different nonmetals bonding together, like, for example, water. And we have a particular way of drawing the structure of covalent compounds by using Lewis structures. Now, to highlight the difference, and we're going to focus mostly on compounds in this unit or in this series of lectures, to highlight some of the characteristics of molecular compounds, these generally exist as separate molecules. And what I mean by that, if we were to look at, say, we had a glass of water and we were to really zoom in and able to see the individual molecules of water, they would not be bonded together. They'd be kind of floating around and maybe bump into each other. Sometimes they might get closer or farther away, but they're not bonded to one another. And because of this kind of sort of weak interaction, molecular compounds tend to have lower melting points and boiling points than ionic compounds. Now, I say generally because there might be an exception here or there where, you might have a molecular compound that has a really high melting point, and that might be higher than an ionic compound with a really low melting point. So this is a very general description or representation. Now, ionic compounds, and we've highlighted this before, but again, just to review, are made of cations and anions. Cations tend to have a positive charge, or cations do have a positive charge, and we find those in the metals. Anions have a negative charge, and things that can develop a negative charge are the nonmetals. All right, like, for example, a sodium cation and a chloride anion. Now, when those bond, these do not exist as separate molecules. In fact, it was highlighted that they exist as crystals or lattices with repeating units. And so a single chloride ion here is not bonded to just one sodium cation. There are plenty of sodium cations around it interacting. And because this is a much stronger, a much more prevalent interaction, ionic compounds generally have much higher melting points and boiling points than molecular compounds. But it would be a mistake or be incorrect actually to call sodium chloride to say, oh, I have a molecule of sodium chloride. No, you don't, because multiple sodiums are bonded to multiple chlorines. Multiple chlorines are bonded to multiple sodiums. So just remember that distinction. And one thing to highlight before we leave this category is it's possible to have ionic and covalent bonding in the same molecule. And we see this when we are dealing with polyatomic ions. So for example, the compound ammonium nitrate that consists of the ammonium polyatomic ion. And notice within the ammonium polyatomic ion, there's covalent bonding. But that whole ion ionically bonds to nitrate. So there's the nitrate, -1 ion. And so you have these two separate ions that bond together ionically. But within each ion, there are covalent bonds. So it is possible to have um, both instances of bonding within one compound. Now, one thing that we have not highlighted or spent a lot of time on are the charges of transition metals. And one of the main reasons for that is that a lot of them can have variable charges. We know that like the first column, the common charge is +1. Sometimes hydrogen's a little weird. Hydrogen can be +1 or -1. We'll talk a little bit about that later. But the second column +2, third column +3, so on and so forth. But the elements in those compounds tend to have one charge. The transition metals, though, almost always have a plus charge, but it can be variable. Copper, for example, might have a +2 charge in one compound, but have a +1 charge in a completely different compound. And these charges tend to range from +1 to a maximum of +7. I can't think of anything that has over +7 charge, but um, some of these ions have that wide range of variability. Now, I do want to point out silver and zinc are kind of exceptions. That's why I'm kind of crossing them out there. They only have one charge. I'll get into that later. But in order to determine what charge a transition metal has, is you have to look at the formula. So, for example, let's look at copper chloride. Now, how do I determine the charge of copper in this compound? Well, first of all, notice that it's not an ion, so that means its net charge is 0. So all the charges of the ions in this compound have to add up to 0. Now, I do know the charge of chlorine. Chlorine is almost always -1. And since I have two of them, that's an overall charge on the chlorine side of -2. That means in order for that single copper atom to balance that -2 charge out, it has to have a charge of 2 plus. So in this case, charge on copper is 2 plus. Now let's compare that with this, CuCl3. Again, it's not an ion, so all the charges have to add up to 0, but I'm going to use the same process again. Chlorine has a charge of -1, and I have 3 of them. That means that's a total negative charge of 3. In order to balance out the -3, copper has to be 3 plus in order for it to add up to 0. So copper here has a charge of 3 plus. Now let's get a little bit more complex here and look at iron. So here we have some compound of iron oxide. And again, how do I determine the charge of iron? Keeping in mind, it all has to add up to 0. So oxygen almost always has a charge of -2, and I have 3 of them. So on the negative side, that's a total of -6. Now that means all the iron atoms have to add up a charge to +6 in order for the whole compound to have a 0 charge. But in this case, I have 2 iron atoms. So I'm going to divide this by 2, and that tells me a charge on a single iron is 3 plus. So in this compound, iron has a charge of 3 plus. Let's look at one more. So iron nitride. Okay, so first concept I have to remember, since this is not an ion, it's neutral, all the charges have to add up to 0. Well, nitrogen is usually -3, and I have 4 of them. So the overall negative charge is -12 over all 4 of those nitrogens. That means all of the irons have to add up to +12. The formula tells me I have 3 of them, so 12 divided by 3 is 4 plus. In this case, iron has a charge of 4 plus.